Okay, problems 3 and 4 from 27B. The first one was this little probability chart that had men and women versus how often they took the medicine the way they're supposed to. Just notice a little difference here. They have actual probabilities in this chart. They all add up to 1 instead of people. So when you're dividing by 1, you don't really have to divide by 1. You can just look at the chart, right? You still might have to do a conditional probability over that, though. So I don't know, I got some numbers up here. The probability that someone's response is never and who's a woman. You just look right in the chart, 0.0636. Probability the person selected never or a woman. So remember, you add up the nevers with the women and then subtract the overlap. So that. And then the third part is the probability never given you're a woman. So there's 53% of women. 0.0636 is the number from the chart there at 12%, which we're going to need in a second, because then we're supposed to find out if they're independent. I think we just had one of these on the last one we did, huh? This one, they turn out to be independent. So the probability of never given woman, says number 12%, has to be equal to the probability of never, which was 12% from the chart. And then you flip it around. You do have to check both. If you got a no here, boom, done. That's why we normally don't check both. But it is possible of one or the other. So probability of women given never is 0.0636 divided by 0.12, which is 53%. Probability of women is 53%. So, since the probability of A given B equals the probability of A, they are independent. Part C says, assuming a large population, the probability that the person always takes their medicine is 54%. 5 people are selected at random from the population. What's the probability at least 4? So you could just add up 4 and 5. You could do the and choose R for 4 and 5, or the binomial PDF, which we'll find each one specifically because there's only 2, so you can just add them up. But I chose to use the binomial CDF. So remember, the binomial CDF adds up from 0 to whatever. So we want at least 4. So I added up to 3. So this is the number of trials, which is 5. The probability of success is 54%. We're going to add up to 3. So this is going to add up 0, 1, 2, and 3. But I want 4 and 5. So subtract it from 1 to get to 24.15%. Question number 4, pretty straightforward test. I would like to think you're probably going to get some sort of hypothesis test, an AP test. Pretty common, covers a lot of stuff, right? So this is the one with the tumbleweed and is it more resistant in 2014 versus 2017. One little catch here, just be careful. They said in 2014 it was 19.7% of 61. If you type that into your calculator, you don't get 12. You get like 12.06. Don't type 12.06 because remember the calculator needs the number of successes. So it's just rounded because that's rounded a tad. So that's 12. That's 20. That's a 2 proportion Z test. 2 independent simple random samples, N1 P1 hat, N1 Q1 hat, so on. There's the 12 plus the 49 to give me the 61, the 20 plus the 32 to give me the 52, all greater than or equal to 10. Each proportion is at least 10 times, or each population, sorry, is at least 10 times the sample size. We've met all the conditions. The null hypothesis is P1 is equal to P2. The proportion resistant in 2014 is equal to 2017. Since I started with 2014, the alternate, we're trying to see if it's more resistant. So 2014 is less than 2017. You could have done it the other way around, of course. It's been a right tail test, all 5% on one side, negative 1.645. I got a test statistic of negative 2.2. P-value 1.35%. I'm in the rejection region. I'm going to reject the null, which means there is evidence the plants are more resistant in 2017 than they are in 2014. That's it on that one.